This is a continuation of 4.3 temperature and heat notes. So we just talked about thermal energy, and for this we're going to talk about thermal expansion and contraction. Okay, so due to thermal energy, objects can expand and contract. Generally, we see this with objects that are in the state of air. It's more apparent compared to things that are like liquids, and even less apparent in things that are solids. So this happens because of the movement of particles. Okay, so the example here is a balloon in liquid nitrogen. And so if we had like this balloon here, and they're going to pour liquid nitrogen over the balloon. Okay, and as they pour liquid nitrogen is very, very, very cold. Okay, and so it's cooling off the trapped particles, air particles within the balloon. So as they cool off, they're going to shrink. Okay, so the air particles inside the balloon are moving very, very slowly. Okay, they're not moving as fast as they were before because they're being cooled off by the liquid nitrogen. So because they're not moving as with as much energy, they're not expanding out the balloon like they were before. So as they let the balloon warm back up, it's going to start expanding because the air particles within there are gaining more and more energy as they warm up, and they're expanding to fill out the balloon. Okay, so that was both examples of contraction, thermal contraction, and thermal expansion. So the balloon contracted because the particles cooled down, they slowed down, they weren't able to press out the barrier of the balloon. And then we saw it expand back out once the particles started warming up and moving more freely. With more energy, they were able to expand out the balloon. Okay, so we see this happening in real life situations with things like cars. So if you're able to drive a vehicle, you might notice that during the winter time, your light might come on that says you have low pressure in your tires, and it's not because you have a leak in your tire necessarily. It might just be because of the cold temperatures. It's cooling off the air trapped in the tube in the tire, and it's causing it to contract. So it's having lower pressure in your tire that makes the gauge or the light come on in your car. Okay, specific heat. This is just the amount of energy or heat needed to raise temperature of 1 gram of material by 1 degree Celsius. So depending on what material we're trying to heat, it's going to require different amounts of energy. Okay, so the unit for specific heat is joules divided by grams times temperature in degrees Celsius. So the lower a material's specific heat, the more its temperature rises compared to the material with higher specific heat. Okay, so the ones with lower specific heat, they don't require as much energy to raise its temperature. Okay, so if we look at this chart here, it shows us different materials and their specific heats. Okay, so water has a specific heat of 4.18, so it requires a lot of energy compared to the other things here on this list to raise the temperature of water. Okay, that's why a lot of the times whenever it's really, really hot outside, a lake is going to actually have a lower temperature just because it's not absorbed enough heat from the ambient temperature to heat it up because it requires more heat to raise the temperature. Okay, things like iron and silver that have really low specific heats, they can heat up very, very quickly. Okay, and that's kind of one of the reasons why we use things like iron or metals to use as cookware, because they can quickly heat up in order to cook our food. Okay, so if we had two bowls, and let's say they're identical, except that one is made of plastic and that one is made of iron, and they're exposed to the same amount of energy or heat, which one would have a higher temperature after 2 minutes? So because plastic has a higher specific heat than iron, okay, the iron is going to get a higher temperature because it requires less energy to heat up. Okay, so we can calculate this. The equation for it is Q equals M times C times delta T. So the Q represents energy or heat, and it is measured in J, joules. M stands for mass. It's measured in grams in this case. C is the specific heat, and this value will always be given to you unless you're calculating it. Okay, so its units are joules per gram times temperature, degrees Celsius. And then our delta T, delta means change, so change in temperature. It's in degrees Celsius, and so in order to find the change in temperature, you're going to take the end temperature minus the starting temperature to find the change in temperature. Okay, I also solved this formula for you if you were to find the change in temperature. So you would take the amount of heat given divided by the mass and times the specific heat. So if we have a pan that is 20 degrees Celsius and we want to heat it to reach a temperature of 45 degrees Celsius, okay, so to find delta T, we would take 45, our end temperature, minus 20, our starting temperature, and we get a change in temperature of 25 degrees Celsius to cook food. The pan has a mass of 2,200 grams and is made of cast iron. How much heat is required? Okay, so using the equation, Q equals M, our mass. So our mass is 2,200 grams. So here I have it written out. Times our specific heat. So if we look at the chart here, the specific heat for iron is 0.449. So I plug that in here. Times our change in temperature, which we already calculated in the problem. Okay, so it's 25 degrees Celsius equals, so we multiply all those together and you should get 24,695 joules.